Okay, 5 o'clock. How's everyone's weekend? Everyone had a good weekend? Yeah, I wish I did. That's okay. That's a bit noisy? I might turn that down a little bit. Sorry. Getting a bit of feedback. Okay. Yeah, so we're up to week 5 and I have to kind of get my skates on because we're going to finish unit 3, but we did it out of order. So I think I looked at it last night and went, oh God, that's a long unit. We're only up to here, but it's fine because we did the last bit first. Then start unit 4 next week and my last one on Monday, which is kind of crazy. We're going to be through it. So we'll quick go through unit 3 and unit 4. Hope everyone's making progress on the homework. Everyone's feeling good about it? Yeah. How much? 48%. Oh, that's okay. If you need help afterwards, feel free to ask me. Remember, we have the consultation hour on Wednesday night. So if you want to join in, because we're not getting many people coming, so you kind of get a lecturer to yourself. Cool. Okay, so back to unit 3. Yeah, that consultation hour. Don't know. There it is. Weekly at Wednesday at 7. It's a bit late, but it's fine. Okay. So algorithms. I gave you just a rough go through of bubble sort. Remember, bubble sort's a terrible sorting algorithm, but it's really easy to understand. So that's why we talk about it. We started going through, just showing some rough idea of like what sort of complexity we think we'd get empirically. How would you show it empirically? That's actually a really hard question. So we're not going to be too fussy on that. But basically, it's just like counting the rate limiting steps is basically what you want to do. And this rate limit, I was saying this comparison function is probably the rate limiting step, and you're going to do that n squared times with a rough demo. So that's kind of where we finished. Cool. Everyone was happy with bubble sort being n squared? Yep. Okay, that's fine. I hope so. I'm going to start this. I just got a question about it, so this is all for you. I thought it would be a good thing to do. In the homework, it has this question about passing a comparison function, and this can seem a little bit weird, depending on how much programming you've done. But you can kind of pass a function around as a variable, and that's a fine thing you can do. And there's various ways you can do it. You can go, so you should all be pretty familiar with all these different ways of setting up. I'll do the long-winded way. My plus 2 of x equals y equals x plus 2. And I didn't put a return, but we can do that. Now type my plus 2 of. So there you get a simple function like that. We could also do an inline version. We go my plus 2 of x equals x plus 2. So same thing, do the same thing as an inline function. Now, another thing you might want to do, which can seem a little bit weird, and I've actually done this before. I've shown you this in the notes, but I didn't really talk about it. So I have this sneaky habit of showing you something before I tell you about it. So you'll get used to it, so you won't be confused the first time I show it to you. But you can set this up as a thing called an anonymous function, where I did this for a map where you can do this funky syntax. It'll come up with this funny thing where it's got like #1 generic function with one method. It's called an anonymous function because it's a function with no name. You can actually pass this, you can have this as a tuple. You might have seen me do this when I went map x goes to x plus 2. When I was doing the equivalent of a broadcast, I went, okay, cool. That's this thing here. This special syntax is how you do an anonymous function in Julia. Again, if you want help, see one of these funny symbols, just try the shift question mark, type through it. Anonymous function mapping arguments s to x to the function body, blah, 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 blah. So you can actually pass something like this as a variable as well. You can do this funny thing. You can go my var equals this, and then I can call my var like a function. Cool. And I can pass that to another function. I can go function, my thing takes x and y, This is going to be, that's horrible, but let's just do it anyway. And if I pass my thing with my var 5. Cool. That's a thing you can do. Has anyone done the equivalent thing in Python with anonymous functions or lambdas, lambda functions? Have you done that? Maybe, no. Anyway, that's a thing you can do. So equivalent thing, we had our bubble sort function here. Previously, let's have a look at what we had. No, I think we called it bubble sort. There we go. So last time we had my bubble sort goes through, goes blah, 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 and the comparison function here was greater than. Cool. So if you want to do something different than greater than, so if you want to sort a list by some other way, like if you want to sort upwards or downwards, you might want to pass in a different direction, or you might want to sort for the data type, there might be a different comparison function that orders the thing. So not necessarily a simple is less than greater than, or you might want to take parts of the struct to do it. So cool. So what we can do, we'll rewrite this guy. Go comp. And again, this prefix infix notation thing, we can just rewrite it like this. And then you can pass a function in as if it was a variable and then use it as a function to do the comparison with. Everyone happy with that? Doesn't have to be anonymous. You can write a named function and just pass that in if you want. It's sometimes, but the thing is you'll end up doing this funny thing where you go like, I think we might even do it in the notes, but anyway. So you can go here. We're going to go data. Let's just see if this works, see if I can copy stuff. So my comp in this case is it's going to do something funky like sum the digits of the number. We're going to sort by like, say you want to do alphabetical order or something funny. It's like, you're not going to interpret them as numbers. You're going to interpret them in some other way. You might want to do some funky thing. This is the sum of the digits. And we're going to go, the comparison in this case, we're still going greater than like this, greater than, less than, but it's a function that takes 2 arguments, num1, num2. We're going to take the sum of the digits and see if there's something bigger than the sum of the digits too. Oh, comp. That's because I called it something else. Let's just check what I messed up. Oh, because this was a named argument. So in the notes, that's why I'm just trying to copy stuff and go quickly. Giving a default value for that. Oh. Let's just see what I messed up. Anyone see it? Ah, semicolon. Yeah. That's what you get for rushing. I'm glad you guys are watching. There we go. So that's why summing by the order of the digits. You could do any wonky old thing you want. Like say you want to do it in binary representation, you could go base equals 2, blah, blah, blah. You do all sorts of funny things, sort by strings, blah, 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 blah. My point was, I had a point, why you would do an anonymous function is you end up doing this kind of funky thing where you go like, I'm going to make a function and then I'm going to pass it directly into this function. I'm never going to use it again. It's a really common pattern. So why would you bother having this thing as a name thing hanging around in your namespace as like a bomb? Like, so you may as well just pass an anonymous function because you're only ever going to use it inside. That's the whole point. So equivalent thing, hopefully you can see this. We've got my comp here. I'll just do it line by line here so we can see it. An equivalent version of this anonymous function is going to be this one. So you're just taking the tuple of arguments. There's no name, anonymous function, like a function literally with no name. It's like really literal in what it's called. And we're going to go sum digits n1. They're called n1, n2, num1, num2 here, but they're basically doing exactly the same thing. The only difference between these two is you're passing it directly into the function without having to define it beforehand. And it's a little bit prettier. You kind of want things to be a little bit tidy sometimes. And say for the examples I've shown you where I'm doing a map to do a broadcast where you kind of, I'm just going to do some weird thing. It only applies to this array. I don't want that function to ever hang around. That's where you do it. Making sense? 50-50? Talk to me about it in the break if you don't understand it, but that's kind of the thing we're going to do. You can do. So yeah, kind of a weird thing is you can pass functions around as if they were variables to functions. That's fine. You can have functions making functions. You can do all sorts of crazy stuff. Yeah, very useful. And you actually see that, I think I talked about this when I said the looking at the docs for sort. Okay, sort, the default arguments, sorry, the named arguments, you can choose an algorithm. You can choose less than equals is less, this by equals identity. So they're kind of following this same, this LT is basically the equivalent of that comp. They've got the same pattern in there because it's such a useful pattern to do where this array might not be numeric data. I might want to do something super weird with it. So I need to pass a comparison function to it. Cool. Okay. Think. Do I want to? I will come back to this. I'll come back to that. I won't talk about it right now. Yeah, so we did this comparison before. Sorry, you might remember all the way back up here. Oh no, where was it? I've lost my place. Okay, yeah. So here, so yeah, built-in sort, we're doing it in milliseconds, whereas the other ones, it doesn't actually look like, the empirical sort of thing is it doesn't look like it's growing like n squared, and it's way, way faster. So it's kind of monstrously faster than the built-in sort is monstrously faster than this bubble sort. And like you could think, oh, it could be software tricks where we're going to go like, oh, we try not to have allocations because we know memory allocation's a little bit slow, but the scaling is never going to be that fast. It's not because of performance improvements and it's not because of tricks. It's because of the different algorithm is used. Might not be clear. I want to say like, this is like, I'm showing you very clever stuff. And one of these things when you're doing your undergrad is lecturers always tell you clever stuff that really clever people come up with that they could never have come up with themselves. This is one of those cases where this is really smart stuff about how you would come up with one of these algorithms. So it's like, we'll get you to reproduce it. It's like, I would have been, you know, you'd be famous if you'd come up with these things because they're actually kind of hard. Oh, yeah? Yep, that's true. That's true, but it's easier than coming up with one of these sorting algorithms, I would say. But that's, yeah, true. It's fair comment. Yeah, I'd take that as a fair comment. So anyway, timing much, much faster. This scaling appears to be n log n. You can do some theoretical stuff. This isn't a theoretical course. You can go off and do other courses to learn this stuff properly, but it's like, there's multiple sorting algorithms. They usually have an average case of n log n and arbitrary data. So this is a big point. For arbitrary data, you can't do better than n log n. But if you know something about the particular data, you can do better. So for example, if it's only a fixed set and you're trying to sort a fixed set, there's better algorithms you can use. You can have a think about how you might do that. We're going to go through some stuff, and this is an excuse to teach you a little bit about data structures. The first efficient data structure we'll go through is a heap, and this lends you this really simple algorithm for doing heap sort, as long as you didn't have to build the heap mechanism yourself. And at the moment, I'm just going to kind of show this to you guys. Later on, I think Unit 7, you're going to build your own heap to do something. So we'll kind of just show you like why this is cool. The idea of a data structure is, I kind of said something about this sort of hand wavy thing about like, you know, data types are really complicated. Sometimes you can set up the data structure itself to help you solve the problem. And that's the whole idea of a data structure. It's like, it does most of the work, and then you can use simple algorithms on top of that data structure. Hopefully we'll motivate this reasonably well. Heap sort's not the best. It's kind of like an open question about what the best is. It's like, in Julia, the default is quicksort, thing called quicksort, which I think is in your homework. You have to do your own quicksort. And so I'm not going to talk too much about that. I think in Python, I might be out of date, but I think it's something called timsort, which is the algorithm they actually use. I don't know if they still use it. The guy who made it for Python. And I think Rust uses something like the same thing. but it's kind of like not clear what the optimum is. That's why I'm saying it's really clever stuff to come up with these algorithms. If you want to look it up, you can go through the sort. Don't know if that'll work. Yeah, anyway, data structures. So, okay. We've shown you arrays and it's kind of boring. Everyone super happy with an array, like a length one array. Going to kind of poke around in the gizzards a bit and use Julia in a way that it's not normally used to show you what's going on with, like, on the hardware. You can see some details about how this is actually implemented on the hardware. One of the things you would want from an array is order one lookups. Other operations are more costly, blah, blah, blah. The reason for this is that we'll just go through this one by one. So we're going to make some data and everyone should be able to tell me, oh, have I shown you this function? L-type? No, someone answered no. No, good on you. This is equivalent to going like, so L-type of data says it's in 64. What this thing is, I've probably done this one to death, is type of data. So an element in the array is type 64. Sometimes you get given this array and you're going to go like, of that array, like what's the elementary type of that array? That's that L type of data. If you had something funny like this, L type data is any. So type of data will be a vector of type any. It's basically giving you the thing in little curly braces when you go.
Julia, if you have something of like an array with
mixed types,
it defaults to any, not like a union of those.
Yeah. That's right. You can coerce it to do that. Like I could go, oh man, data equals. No, sorry. Yeah, then I can go push. Oh, sorry. You're an annoying thing. And I can do that way. And then if I go L type data, so it's a small union type. But yeah, the default, so you don't have this annoying constructor problems and you don't have to think about it and you type 2 instead of 2.0. Like it's kind of easier most of the time to just default to any. This will come up again probably in the next section. Claire will talk to you about all this stuff. But yeah, good question, great question actually. Now I've got to get it back into my state. So, oh, don't want that one. That one. So L type of data is an int64. Size of L type of data, what's this going to be? What's that going to give us? The size of bytes of the elementary type. Anyone know what that answer is going to be? So how many bits in a byte? 8. Yep, so 64 divided by 8 should say 8. Cool, that's the size of everything in size of is going to be in bytes. What we're going to do is we're going to go pointer data. So this funny function give you the native address of an array or string, or optionally blah, 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 blah. So this will tell you kind of like an address for where this bit of data is in memory. So you can get at this stuff. So there's a separation. I mean, they're all high-level languages, but there's kind of a big gulf between ones where you have to muck around with memory management, languages like C, C++, and then ones where you kind of don't need to worry about memory management and you're going to have a harder time, an easier time, sorry. Much easier to write programs, like say Python, Julia, blah, 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 blah. But if you want to go mucking around, you can totally do this. And that's why it gives you this warning that this function is unsafe. Like I can go pointer to this array and then I can get rid of the array and then I can go to that bit of memory and I'll read some other bit of data. That's not really what you want to do. So like this is a very low level operation and not typical of what you'll be doing when you're mucking around in Julia. But we're showing it to you because we're going to show you pointer data. This is where the address of this memory, you've got some hex string here, blah, 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 some big number. That's where data is in memory. What do I want to say about that? Okay. Not much. So the next bit is, where is the first element of data? Where's the pointer to that guy? And that's same place. So it's actually pointing, so the first bit of data in data is at the same address as data. Ah, man, that's an awkward sentence. Then the next bit is going to be 8 bytes away. We see that guy's incremented by 8 because that size of the type is 8. So they're kind of next to each other in memory. So if I go to the third element, again, should go up. Oh, sorry. I jumped. Oh, wait up. I've lost track of what I was
It's right. It's just hex.
Yeah, it's just hex. Okay. Ah, yes. I've got to count A, B, C, D, E, F. Yes. Good. Thank you for it. Yep. Cool. That's why I did the next one in a different data type. But yeah, so you can see these things are always 8 bytes away from each other in memory, laid out next to each other in memory. This is kind of like a common thing because it's fast to access memory if it's next to each other. Whole point is you want to address this. Usually when you're working with an array, you're going to want to get the next bit of data really quickly. This is a really brute force way to enforce this. Yep. It depends. It depends. So like it's you kind of don't want to resize every time you push because then you're going to get this like grow it. So it'll do like a logarithmic sort of thing in the guts is what I understand it to do. I don't know exactly what the details of it are, but that's a really good point because like reallocating memory is going to be slow. You've got to kind of try and find a chunk where it's like big enough and you've got to make it fit. So it's a bunch of work to do. That's kind of why these resizing operations will kill you. Cool. There's lots of different data structures you could do. Go and if you're an advanced person, you want to go off and read off more, go look at linked lists, queues, stacks, blah, 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 blah. Okay, big question is what happens with multi-dimensional arrays? So we talked about this and like the most common one would be a matrix. So kind of got this weird choice. Let's do it this is why I did this one this way because I'm too dumb to count in hex. It's kind of funny, I tricked myself. So we've got an array, just random. We said they were int 8s this time. So this time I can count in bytes and I'm not going to get confused by them jumping with hex. So they should just be 1 byte away from each other if it's an int 8. And you kind of got to, I've randomly just, this undef will randomly pick bits and we'll just see what's there. What we're going to do is we're going to iterate through this linearly. So every array like this, I can go data 1, 2, 3, 4, 5, all the way up to 12. And then if I go 13, it's going to, well, how big did I make this thing? 15, 16, sorry, missed the size, 3 by 5. So if I index outside the array, but I'm only indexing with 1 element, this is the thing. I can also index, which is much more natural, like you think about it like a matrix. I can also index it with 2 coordinates, but underneath it's really doing this linear indexing. And I want to show that. So this will be different than, we'll go through, iterate through. We're going to show the pointer going over it sequentially. And this time it'll go, and I won't get confused by the hex, it'll go 8, 9, A, B, C, D, E, F, 0, 1, 2, 3, 4, 5, 6. So they're all right next to each other because this time it's an int 8, not a int 64. Cool, so they're all next to each other in memory and you can see something about the pattern. So yeah, this is showing if you wanted to convert this double, this double index into a single index, you would do this equation. So that's the point of that. This has kind of got names, different names. It's like this, I'll just show you. So just to make this super clear, you've kind of got an arbitrary choice about which way you will lay out the data in memory. You could go columns go quicker or rows go quicker. Rows go quicker or columns go quicker. I don't know which way my hand goes. But you could, it's completely like, I can hope you can understand that this is completely arbitrary which way you would choose to do this. And of course, because of this, different languages have done different things. So Julia has gone for column major. So the fast direction, so the things next to in memory are down a matrix, and then it jumps up and goes down again, jumps up and goes down. This is kind of a common pattern for scientific numerics libraries. They'll nearly always be column major. There's probably a really good reason that I don't know. But so Fortran will be column major. I think NumPy is column major as well. But if you go to other languages like these low-level languages like C, the bare C arrays, the normal C arrays will be actually the other way around. They'll be row major, except if you use a numerical library in C, and then they go back to column major, like Eigen. Has anyone come up with used Eigen before? Might come up in your future if you ever have to do numerical stuff in C++. It's a common library. So I hope this is clear. You've got this choice. Julia's gone for this way. Cool. This has a kind of terrible consequences. So there's the theoretical pattern of this thing where array access should be order 1, but there's order 1 and then there's like second-class citizen order 1. And this comes up if you have really weird shaped arrays. Because of this thing in memory. So a computer is going to be much faster at getting things that are right next to each other in memory than things that are far away. So I've kind of constructed a really pathological example here where I've got two functions. I'm going to sum over the rows and I'm going to sum over the columns. So basically this guy will take data and the size. I shouldn't have to take the size, but I was just too lazy to do nm equals size. But it would have an accumulator that goes, this is 0 of that L type of the data. So whatever matrix you pass in, it's going to get the L type of that. And then it's going to iterate over the difference between these two is like J goes first or I goes first. This is in the same order. So we're going to go, which way are you iterating fast through the matrix? Is it this way or this way? Make sense? Cool. Everyone happy? Okay. This is actually kind of funny. So I've made a really pathological example here. Let's just run it. I'll run it. Shouldn't take too long. So did some timing stuff. We'll leave that running in the background. But we're going to make this really wacky size thing where it's 500 by 1,000,000, N and M. So it's like really skinny and long or really long and skinny. That might come up. I mean, like you might have a matrix of that shape. It's kind of not that unheard of, but I'm just trying to push it so I can actually show this thing. Cool. So just to show I'm not lying to you, if we do sum over the columns first, and remember Julia's column major, on this computer, so Yoni's got a better computer than me, obviously, because he got 0.6 seconds. And order of 7 seconds, so it's order of 10 times quicker to just sum if you're going via the columns first than going via the rows first. That's because of this array memory thing. So even though it's order 1, if you've got to do a big jump, it's going to do cache misses and stuff, and it's going to go really slowly. This will come up, like if you're trying to do stuff that's really fast, thinking about the way you iterate through a 2D array or a multi-dimensional array even will make a difference because you kind of want to match up with the fast way for memory access. Happy? Cool. If it's more benign, like if it was like 1,000 and 500, it's probably going to be exactly the same. We can try it. Let's do it just to see. And so 0, 0, it's actually summing over the columns was actually slower, but timing was pretty poor. Like, so, basically the same time, but if it's really long and skinny, you have to worry about this stuff. Yeah, cool. Dictionaries. Next data structure that's a useful one. Has dictionaries come up for anyone before? Everyone who's not familiar? Not familiar? Okay, this is a super useful one. I kind of said this thing about types and structs, and I've basically shown you a few little structs and I've kind of gone like, data modeling is like the hardest thing. I honestly think like in software, getting the data model right is probably the hardest thing to get correct. So this sort of useful thing when you don't know what you're doing is this thing called a dictionary. It's this super flexible thing that has keys mapping to values. So it's kind kind of superficially like a struct, but it's much more flexible because it's mutable. So you can change this thing. So when I'm prototyping, hasn't come up for you guys yet because you're probably not making, anyone in the homework made their own struct to do anything yet or not? No, probably be the next one. What, you did a dictionary? Yeah, good idea to use a dictionary. Dictionaries and sets, definitely try those. When I don't know what I'm doing, when I'm prototyping, I'll often make dictionaries to sort of prototype the structs until I can kind of work out what the type is. And then when I've done it a couple of times, I go, oh yeah, it's that pattern. Unless it's obvious. Dictionary is this really useful thing, built-in type. The syntax is a little bit funky if you're not seen it before. So this annotation is basically it's saying the key type is a string and the value type is an int, 16. Again, you know, if you don't know what that's going to be, like if you're in prototyping land, you can go any. It's a string mapping to any. It doesn't have to be a string as well. It can be any type. We can make one of these guys, dictionary of postcodes. This is the way you put it in. You can go, you put the key in with this value. You can construct this in one go. If this is a bit more painful, you would go something like CR goes to 4067. I don't know. I don't want to type. It's got this funny syntax though. So I just want to do it so you see it. Sometimes you'll see this arrow like in data frame constructors as well. That's the way to make it in one go. You might have two arrays is another one that's really common. You might go A, B, C. That's another way to do it, just to show you some of these ways. So that's useful to have keys and values. What else are we going to do? So I'll just show you by use. So if you want to get the value back, you just do this array access is one way to do it. And it'll give you the value. If I try and put something in there that doesn't exist in the dictionary, it'll go error. So if you want to be like a little bit more systematic, you can do get dict Hobart. So this is probably a little bit more, a better way to do it is if you can go, I want to get Hobart from the dictionary. If Hobart's not there, I want to give nothing. So it'll give nothing. That's another way. You can also do, this is a very useful predicate function. So if you want to do a bit of control flow, you can do has key Hobart false, whereas has key, can I type? Oh, did I type it wrong? What was the keys? Oh, if I don't know what the keys are, I can go keys of dict. That was Saint Lucia. True. Cool. I think that's it. Has key, get. I don't think there's anything else I wanted to say about that. Oh yeah, you can, same thing. There's keys of dict if you want to just get the values. Values, you'll notice these guys came out as funny types. This guy comes out as a key set, and this guy comes out as a value iterator. So this same thing of like before when I did this thing, 1 to 3 type of, it's this funny unit range thing, like because you don't actually want to make the array. I just want to make a function that will like yield the next one when I ask for it. Similarly for this dict, when you go like, if I get keys or values, I'm going to get an iterator that'll go through it. So that's probably a useful one. Show you this for key. I always do K and B. So if you want to iterate through it, you do KV in a tuple, show K. You want to iterate through keys and values. So similarly, if you do this keys function and you want to have it as an array, collect then you've got the actual array vector rather than an iterator. Cool. So that's really useful, but it's only useful if it's fast, I would say. So like there's an important thing of this, maybe we notice this. So dict, when we constructed it, we put in St. Lucia, then South Brisbane, then Rochdale. See, these have gone out of order. So it went Rochdale and St. Lucia, whereas we did them in the other way. So this wasn't guaranteed to actually work. So first, St. Lucia, South Brisbane, Rochdale. Who's got a good memory? South Brisbane, Rochdale, St. Lucia. There's no guarantee that these things are going to be in the order you put them in. So this is one of these funny things about dictionaries. You can actually have an ordered dictionary if you want one. Julia, they're going to be out of order because it's kind of a different thing. It's like a dictionary. It isn't like a dictionary. It is a dictionary. You don't really care about the order the keys go in. You just care whether it exists in there or not. So when you go to do one of these iterators, don't expect them to come out in the order you necessarily put them in. There's no guarantee that's going to happen, as a warning. Super useful. How do you think you might implement that? Anyone got any crazy ideas? Yeah. Yeah, as like an array, backed by an array. You could just totally do this by array. So this little demonstration here is you could make a struct that's like, it's got keys and values and they're just arrays. And if we add a key, we're just pushing the key into this key array and we push the value into the new value. Problem with that is it's really slow. So if you're going to maintain this thing as an array, super slow to do this. And the whole point of dictionaries, I guess, is that this dictionary access pattern is order one, like an array. So like even, it doesn't matter what it is though. It's like I can access this with a string. It's not an array index and it'll be really fast to get the value back. This is implemented by this thing that we're not going to talk about, but I'm just going to point out called a hash table. So average case complexity for insert, delete, and search is order one. Worst case is order n. So most of the time it's order one. So like if I want to check, this one will come up for you guys, but I'll do it in the sets example, but made this guy. Say this was really big. So the dictionary started to get really big. So we're going to go up to 1 million, say. So 1, 2, 3, 1, 2, 3. And YY equals. This is a stupid example for the data in it. So I'm broadcasting 2.0 times XX to make Y. So this is his other array. If I go D equals dict zip XX YY. So, so I made it as arrays. Oh, this is getting more complicated as I go because I didn't plan it beforehand. So just imagine I'd made two big arrays going up to 1 million and 2 million. Oh, 6. I'll make this. There we go. That's the one I actually wanted. So if I go D, 1 is 2. So if I'm going to search for if I had an equivalent thing, so if XX is this guy, if I go 1 in XX versus has key D, so these two operations. So for this guy, to check whether this guy is in this array, it's going to take a long time because it's basically searching through the array to see if it exists in the array. If I do the timing on these guys, we might not see it. Do it 1,000 times. Do it. Lots of times until it gets slow. So it's taking 0.3 of a second, where if I go has key. Oh, that's the same. I'll come up with the example in the break, but yeah, it might be. I'd probably better off. I'll come up with a better example in the break, but the array access one, especially as the arrays get big, having to search through the array is always going to take a long time. So it depends on the implementation for in. I'd probably be better off to pick a random element of. Let's see if this one works. There you go. Bonus points for you because you figured it out quicker than I did. So you see the difference between that. It's like taking forever now to actually find it. So the whole point of dictionaries is that this, yeah, so it's obviously searching from the front of the array. If you pick somewhere in the middle, worst case would probably be at the end of the array. It's going to take forever to actually find this key in the thing. I'm going to kill that because it's taken too long. But you get the picture. So the whole point of dictionaries is they're much more clever than just having it backed by an array. The whole point is this special data structure that lets you look things up in order one time. Natural extension of this, this one, if you want to, Andy used to teach this course, or he still teaches this course, he's taking this year off, but he has an alternative implementation that gives you like nice ordered properties. He actually made an alternative dictionaries package for Julia. You can go watch this YouTube lecture of alternative implementation for dictionaries, recommend it if you want to learn a little bit deeper about how far down into hell you can go with this stuff. Okay, cool. So maybe someone's really bright. The answer's on the side, so just to pretend you didn't see it. If you have a dictionary with just keys and no values, it's equivalent to a set. So you kind of get sets for free with the implementation of a dictionary. So a set mathematically is like a bag of stuff. This is not mathematically, this is my heuristic version of it. A bag of stuff that's like, it's like no replacement. If I try and put the same thing in there, it doesn't get a new thing, but it's unordered. So this unordered thing, collection of things, and you just give it an ID. You want to kind of, with a set, all you kind of want to know is like, is this thing in the set? If I take the union or the intersect of the sets, I want those operations to be quick. You can actually do this with a dictionary. You just have a dictionary with no values. So all the values map to nothing and you just get the keys. That's how you would implement a set as a data, so you get this nice, useful mathematical thing kind of for free with dictionaries. So this will be built into most programming languages. They'll have or high level ones will definitely have a thing like a set. And if you look into the implementation of a set, might not say about the implementation. No, it's not going to do it. It's just pretend it's a mathematical set. So same with dictionaries, I should say, is like, if I have this dictionary we put in before, if I try and put the same key in twice, it will obliterate the one that's in there. So it doesn't get repeated. It'll just get obliterated. So you only get one key per value. That's the constraint. So similarly for sets, if you have a set, what's that? Oh, one key. You only get one. Keys have to be unique. There's a better way of saying it. Keys that must be unique. So this thing with a set, you notice I've put in an array here with 1, 2, 3, 4, 1, 2, 3. What we get as the actual set, don't know if I did this. My set only has 1, 2, 3, 4. So these things, even though you're trying to push more stuff in there, 1, 2, 3 again, won't go in there. It's just like collection of stuff. If you want the mapping of your normal set operations, you get these functions union, intersect, set diff. Set diff depends on the way around. Constructed with an iterator, just to make it a little bit more confusing. So we've got A and B. A has 7, 2, 3, 1, 2, 3, 4, 5. If you go set diff A, B. Get a different answer if you go the other way around. Set diff BA. Just make sure that the order is important when you're doing set diff. What's in this set that's not in the other set. If you want to do the symmetric difference, you would do this union. So again, you can do union, set diff, intersect, then you can kind of create all the things you'd care about. Yeah, so this is a really useful one. So maybe this is a hint for a way to implement something in the homework, not sure, yeah? Sorry? You can try. Have the set of all sets that don't contain themselves as members. See if you can set that up and see what happens to your computer. Might become self-aware. So yeah, so this thing, if you have an array of stuff, it's not an array, and you just want to check if something's in there, but you don't care about where, this is a really useful data structure. So who can come up with an example of something you might care about for that? Like something you might construct once and then go, I just want to check if this thing's in that list. I don't really care where it is in the list. What's that? Password's one. What about in the homework? Who might think of something? Yeah, so if you set that up as a set, it's gonna be much quicker than searching through an array. That's a hint. So depends how you set it up. That's one hint. That's one way of being tricky to do that one. Cool. There's better tricks, so it's not that big a hint. So similarly to this thing, this bad example I was trying to do before, if we do set inclusion in an array, I should have read ahead in the notes, just sort of ad-libbing, but they're doing another example. I did this, I don't even know why I didn't think of this, but so we'll pick, yeah, this is the same thing of checking oh, I've forgotten what the symbol for that one is, but it is in, is it? Yeah, cool. You know what you're doing. Yeah, so that's equivalent to in the function. If you do this, so we've got array data and a set. If we run the timing for that similarly, like the set one is super fast compared to this, to do with this implementation of a hash map. Cool. I'm going to do a little diversion about dictionaries and data types. I want to say I'll just do this really quickly and then we'll take a break. I think may live to regret this, but I'll do it anyway. Okay. There was a question before about comparison functions I think we're in a good spot to do it because we talked about dictionaries. What was this one? The comparison function. Yeah, I do want to do this. So I said, prototype structs with dicts. I did this, say I want to make my own data type. I could make a dictionary. Like if I keep doing this pattern, I'm going like, I'm always putting, I think what the thing I'm making is I want to call it a person, and every person has an age and a name. If I want to more formalize this and use some more machinery of Julia, I can make a struct. So I can say, if I was giving it this key age every time, and it was always a float 64, and I gave them a name and it was always a string, I might want to make this thing called a struct. So, higher order data type, really useful thing to do. If I make P1, say I want to insert some people. I want to create some people. So I've got a person who's 24 called John. P2 is a person who's 42 called Mary. P3, person, 56, Scott. So bad with coming up with names with these things. And say my data now equals, I can make an array. This was this comparison function thing. I'm going to do a more advanced example for you. So data equals person, Mary, Scott, John. I've got an array of vector person now. That's cool. If I try to sort this, what's going to happen? Yep. So cool. No method matching, blah, 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 blah. So that's cool. So if we were doing it back in this way, we could go, well, A is an array of type person, and then I'm going to make some comparison function that depends on the details of the thing in the struct. I can kind of short circuit this. And this is an example of something called single dispatch. So most languages can do single dispatch. When you go further on the course, Julia can do multiple dispatch, which is like kind of the fancy thing for Julia. But I'm going to give you an example of single dispatch and when that's useful. It's useful all the time. So that's why most languages can do it. I can hijack bases is less. So when I do this less than operator, I can say, well, I'm going to do it be ageist and say person X is less than person Y if their age is less than person Y's age. That's ageist, I'm sorry, but I'm old, so I've got to do that. So base has this special built-in function is less, and I'm going to say it doesn't have a method for my type, so I'm going to give it a method for my type in the method table. Okay, now by magic, I hope, I can sort people now. So this is a kind of like, I can do these long range things in Julia by just overloading, or not really overloading, giving an extra method for this function for my type. So that's like another way of, instead of doing this comparison function, I can just use the built-in machinery to give it a value for my type. I have to be a little bit more clever about what the array type is, but this is an example of single dispatch. And so Julia's magic trick is you can do multiple dispatch, where this is kind of multiple dispatch because it's on 2 arguments, but it's kind of cheaty. But yeah, cool. That's an example of something cool trick you can do in Julia. Wouldn't be how I'd do any of the homework, but I thought it'd be good to see it now that I've talked about that sort of stuff a little bit. Okay, I'll take a break for 10 minutes, unless there's any questions now. No? Happy? Cool. Everyone ready to go? Happy to go? Yep, cool. Oh, no questions on that bit. I'll just continue on. So we'll just forge on. I'm getting through it. I'm conscious of the time, so trying to get through this section quickly. Very much happy to come back if I've gone through it too quickly. If you after the lecture, you go like, I really don't understand what you're on about there, Paul. Just let me know and I'll go back over it. Yeah, it's just meant to be fast, just to introduce like, so big ones are, I think, knowing how arrays are actually laid out in memory is a big deal. Knowing these like more complicated data structures that'll help your life, like dictionaries and sets, super useful, the operations you'd want to do on them, and the performance consequences. So actually, I'm going to tell a naughty story, and someone I work with didn't realize that dictionary set access was so much faster than array access at work. And he was writing these things, and yeah, it was kind of funny. The senior developer didn't realize that that thing I was trying to demonstrate about set access versus array access, the set inclusion is so much faster. So it's a thing, good to see it, so you know it later on. Okay, so fundamentals of algorithms is a huge, huge field. I'm not even the right person to teach it, but it's kind of, you want to see these things so you know what they come up. This one's going to come back in this course, is this one though, that's kind of super useful. This is going to be like a motivating example for it. We're going to use the built-in machinery from Julia rather than trying to implement it ourselves. So we're just going to talk about, where does this thing come from? Why would you care about this data structure? And not going to say about how it's implemented, but we're going to use it to show it gives you a really, really simple algorithm for sorting. That's the whole point of this one, this thing called a heap. And overloading in terms is like really thing. There's two things in computer programming called a heap. One's a special place in memory. You talk about allocation to the stack or the heap. I'm not talking about that. We're talking about a special heap data structure. There's lots of ways you can do this. This will come up again. If you're implementing it as an array, there's a thing you can do, but I just want to show you the picture. It will come back up later in the course. I think it's unit 7. Let's just see if I'm lying to you. Random numbers. Maybe I should just... Yeah. So there's stuff about heaps in here. Unit 7. It'll come back. Cool. So what's a heap? Why do we care? I care because of priority queues. This has been a thing that's come up again and again. Priority queue is a super useful data structure. Like when you're trying to do simulation, particularly just a whole field in operations research called discrete event simulation, where you can kind of imagine, just little agents interacting with things and changing states. That's kind of like with events changing states. That's kind of like a really common simulation paradigm, and the whole big software companies build around it to do simulation of physical systems. You kind of want this idea of a priority queue. Okay, so there's an example, because you can tell this course was made during COVID, where it's talking about mass vaccination, but it could be anything. You could be like, queuing for a server, like an actual literal computer server or a human server in the supermarket. You've got this thing where there's people lining up and they dequeue. You've got like this, everyone's familiar with a queue, and you've got these kind of queue operations that you care about. So, if you're waiting for a music event or something, the big thing is that the highest priority thing from the queue, you kind of always want to know what the highest priority thing in the queue is. Like, what do you do next? So that's where it comes up in simulation. It's like, you're going to go, got this massive stuff that could happen. What's going to happen next? And you kind of want to, if you want to do that, you kind of want to add things to the queue at any time. You want to always be able to add things to the queue. You want to remove things from the queue with the highest priority. You only care about the highest priority thing. It's like, what do I do next? I'm single-threaded. I just care about what's going to happen next. Then if you have the queue, you want to be able to go to an individual and modify, or a thing in the queue, and go and modify its priority. So like you can go, part of the state evolution of this system might be, when this thing dequeues, it changes the state of something else in the queue, or something else happens that means they dequeue. They're kind of the three states. That whole data set thing is like called a priority queue, and it comes up all the time. I have implemented one of these in my professional life. And making it efficient is like basically the whole thing is like, you want this thing to be super fast. It's like fundamental data structure and you want it to be really, really, really fast. We're going to go through a naive implementation. We've got some examples that are similar to the thing I did before, but I think I've shown you these guys before. What's the type of person A in this case if I use this? Anyone remember what this thing is? No? No, it's not a struct. This is like the lightweight version of a struct. So I kind of maybe I should have done my little demo after this, but kind of the hierarchy of these things is when you're prototyping is you'll go dictionary, because I don't know what I'm going to do. Then if you kind of got a bit more of an idea what you want to do, but you don't want to commit, you do this thing called a named tuple. So person came up once before in the notes. So it's a name tuple and there's a name priority with a type and another name, another field. I think I was saying like you'd access this like priority. If you want to know what's in there, I think it's field names. Oh no, it's not field names. Oh, ignore that. I think that's for structs. But you've got priority and name. So yeah, name tuple, useful thing. So again, it's just the setup is you could just totally not have the keys in this one. So it's sort of like a dictionary as well. You could just go, cool, it's Lena. And I just have to rely, because it's tuple, I have to rely on the ordering to tell me what things are. But if you want more of a hint about what's in there, so you don't have to access it like person B, 1, 2, that's kind of annoying. Person B, priority. The access should work still. Yeah, you can still do it by the index, but if you want kind of like a bit more structure and you're less likely to get it wrong if you get the order wrong, you can put this name in there. So we're going to make, what are we doing? So yeah, we can just, again, we can do all this thing really simply. Like we said, we could do dictionaries with arrays. You can do everything with arrays. There's just a consequence. And the consequence of this one is going to be pretty much exactly the same, that everything goes really slow. So we can do this funny bit of type annotation. We're going to say there's a naive priority queue. That's an array. So this syntax where it's square brackets, everything before that is the type of the array. And this type of the array is a name tuple with the names priority and name, and it's a float and a string. It's kind of disgusting. That's kind of getting to the point where you may as well make a struct, I would say. Yeah, naive priority queue, it's got these things. So again, if you go L type, naive priority queue, it'll give you this guff out the front. So it'll be this horrible big long thing. Name tuple, it's got this funny macro for name tuple construction. That might be useful for you too. Okay, so we can, these operations of, I was saying, like, you can consider what the ideal priority queue is you want to add and remove the highest, add people to this queue and then remove the one with the highest priority. Similarly to arrays, the operations are push and pop. Those two things are called, tend to be called. So again, with an array, you can just do, so we had push, naive priority queue, person A. Oh, if you can type. Push, person B. Then if we have a new person come along with a different priority, okay, So each of these guys have got a priority. So the problem with this implementation straight away is we said like the next one is if we want to pop. If we pop just this array, what are we going to get? The last thing put on the array. So like the array will just like get the last thing off the back. So you get Yarden was the last in, first off. And then if you're going to get, they're just going to come out in the way they came in. But we actually want them to come out in priority order. We've got to go through all this again. That was silly. So we're going to have to set up a function if we want to do this to actually give us the highest priority one off. Yeah, this is, I think this was your question before. Push, if you're going to reallocate memory, is going to be a problem. There'll be some, it's not going to be as bad as every time it's going to reallocate memory because that would be atrocious. It will do some clever stuff in the back to deal with that. So again, this is really similar to before. If we want to remove, like we said, we wanted to, or another operation is we might want to delete. So that's another one. So if we're going to go, we're going to find a named person in the array and remove them, that's going to be costly because similarly to the set one, it's not a set, it's an array. So you're going to have to search through the array to find it. So basically, you would have to do something like, if we wanted to remove Zach from the array, we're going to have to do something like n.name. You don't have to do it this way. So if we wanted to get Zach out of the queue, we've got to find the index, that's that guy. And then we'd have to do something like delete at naive priority queue 1. So that searching is possibly slow. You could make it fast by doing some tricks, but it's kind of a hint that these things you want to be fast, they're not necessarily going to be fast if it's backed by an array. Here's an example of finding the next highest priority. This will be a similar thing. You're going to go through the array, go through this priority queue and find the person with the highest priority queue, highest priority. This is kind of a long-winded way. You could do this with a comprehension too. You could go, if you wanted to find the highest one, you could go n.priority. And then I can do argmax. So that would be number 2, is the one you want to get out. Hopefully that argmax is like the mathematical argmax. I don't know if I've shown you that before. Sometimes you want the index for the maximum value is a really useful thing for arrays all the time. Another useful one would be, so its dual, I guess, is maximum. So the maximum priority is that, and the index at which that maximum occurs is the argmax. Yep, that's cool. That's enough to say. So you can do it in one line with this kind of thing. You could do an argmax over a comprehension. So if you wanted to get the next person, you could return, put in this thing and you could get the guy out. That's the way of doing it. This is really slow though, because you're constantly searching through this array for both of these operations. Like if you want to delete someone, you got to find them to delete them because you need the index in the array. If you want to get the next highest priority, you've got to search through all the priorities to find the next highest priority. That's kind of disgusting. And those are order n because you're searching through arrays. Anyone got any ideas about making that quicker? If it was an array-backed priority queue, you could use a dictionary. To find people would be fast, but to find priorities would still be slow. If it was array-backed, we'll restrict it to if it's array-backed. What's something you could do? Is there a trick you could do that would make the other two fast? Oh, you go first. You could put them in buckets, or there's another trick you could do, maybe. Yeah, you could put them in insert. You could make the insert slower by making sure the array is always sorted. Then searching through a sorted array, it's another trick for homework. If you have an array that's always sorted, there's a there's a function in sorted. This is a much, much faster. If you're going to find whether an element's in an array and you know the array is already sorted, there's a function for that. Instead of in, you can go, this is in a sorted thing, be much, much faster because you can do like a bisection search and speed it up way, way more. That kind of gets it from order n to order log n if you do that sort of trick. But again, you've made insertion slow. So that's not kind of ideal either. So you've got, if you want to make, yeah. So we've kind of horse trading here where we're going like, well, insertion's fast because you just push it in, but then dequeuing and deleting, popping from this thing is going to be slow. So we could mix it around and go, well, we'll make insertion slow to make the other two fast. So that's kind of a trick. Kind of you want best of all worlds, which is this thing called a heap. Heap data structure is based on a tree, and you're going to implement this yourself, but just believe me when I say finding the maximum now is order 1. So for priority queues, you always want to know what the biggest thing is. I've got an order 1 operation. It will always give you the biggest thing. And this is kind of cool though, is deleting is log n, insertions are log n, and updating a priority is log n for all of these operations. So we kind of got win for all those different operations where if it was array backed, we're kind of losing. And what we can do is kind of trade stuff off for one another. This is actually unit 7. That's why I kind of wanted to look. We're going to use it as a black box. So this is really easy, right? So this is a thing called heap sort. So this is our first example of like, we showed you order n squared sorting by doing this bubble sort where you just keep swooping through and swapping stuff. This time we're going to be more careful. All we do is, this is the dumbest thing in the world. We push onto the heap and then we read them out. And because we read them out, they come out in order. So it's just 2 loops. So insertions are log n, and then we're going to pop them off one at a time. So this, when you do it together, you're going to get this order n log n thing. So I'll just run it, show that it works. Oh, I didn't have data structures before the lecture. Luckily the internet's quick. Yeah, so hopefully so the particular type of heap in this case is this thing called a binary min heap. There's lots of different types of heaps and ways you can implement them. Again, if you want to, you're going to do it later on, but if you want to go down the rabbit hole of all the different things you can do, and there's a zoo of data structures, it's all very, very interesting. I recommend going off and reading about it. We're not doing it here. All we do, yeah, so we set up an empty binary min heap. We go through this array, we push into the array, then write it back out in order. Hopefully that's done. So seeding the random number generator so we can kind of get a bit of determinism on the things we create. Heap sort A, push in. So we can do these operations one at a time. I think it's kind of worth it. Why not? Just to show that what these operations are doing one at a time. So we've got data. I'm going to create this guy. Oh. The binary min heap of type int64. Depends on the type. And what we're going to do, we're just going to push the elements of this guy in. So this is equivalent to going like data 1, then data 2, then data 3. We'll see that after we do that, all these insertions, we've got a thing. Thing I want to show you though is not the, should have called it E. So H is a binary min heap and it's got this stuff in it. That's a kind of a hint about what's going on. The real big thing though is if we pop from the heap, we get 1, we get 12, we get 23. Everything is in order from lowest to highest until there's nothing there. So little trick there though, is bounds error. If you try and pop an empty heap, you're going to get an error. So it's kind of, the data structure's done all the magic for us. We've got a fast sorting algorithm for free. It's like, that's like the easiest code you're ever going to write because you didn't have to write push and pop yourself and set up this data structure. So you're kind of using the inbuilt stuff. I won't belabor this one. So yeah, what are we doing? So similar to what we did before, we're going to get random data. We're going to do a range of things, and we're going to time the difference between heap sort. We're going to time heap sort. So this thing is somewhat linear for small arrays. So this time, you notice we definitely saw quadratic behavior when we were going through the analysis, like the rough data processing, data fudging sort of analysis for this thing. We sort of saw quadratic scaling, and this time in milliseconds is we're going up to, 1e to the 6. Hopefully that's right. And we're still only like a couple of hundred milliseconds. So it's pretty fast for free. Isn't that cool? How does it compare to built-in sort though? We're going to do the same thing. This is all basically exactly the same. The only difference is we're timing. We'll do the heap sort. And we've got some funky stuff here. Has anyone seen this GC enabled equals true? Has that come up before? Don't worry about that. That's basically just like flushing memory. So there's a thing called a garbage collector in Julia. When you allocate memory, instead of it hanging around forever and eating up all your RAM, you kind of want to trigger that garbage collection. There's kind of tricks for, it's meant to be automatic, but if you're kind of doing this rough timing stuff, you kind of want to trigger it yourself. That's what this little bit of nonsense is. I wouldn't worry too much about that. But, there's kind of scaling the same way. We kind of know from those elementary operations, like how long does insertion and popping cost? We kind of know it's n log n. So the difference between these two is the scaling coefficient. So heap sort is not, it scales well, but the offset is big. So it's still got this same asymptotics, but it's not going to be as fast. But scales the same way. So you can feasibly do, if you try and do bubble sort with 1 million, maybe has that come up in the homework for anyone trying to do bubble sort with too big a number? Or any of the sorting things, you start getting the number too big, it starts to get infeasible. Bubble sort will die because it's quadratic at that time. Those sorts of ones, you can't feasibly even sort an array that big. Cool. So that's 620. Any questions on heaps? Priority queues are super useful. That's like I was saying when I started doing this section, is like, I haven't had to implement a sorting algorithm, but I've definitely had to implement a priority queue in this discrete event simulation thing. It's much more common for my applications. Cool. Okay, so big class of algorithms called divide and conquer algorithms. So I think the meta point of this stuff, like the teaching point, trying not to do things more than you have to is kind of the ideal way to make this stuff faster. So this kind of happens for free in the heap sort, is like when we do insertion, we're kind of doing this clever data structure that puts things in so you always know what's next, what the next biggest thing is. When you're just trying to do more generic sorts, like you kind of want this idea that the rough idea is that you don't want to do comparisons more than you have to. So when we're doing bubble sort, we're kind of comparing everything to everything every time. So like that's why you get this comparing everything to everything is n squared. We don't want to have to compare things to things if we've already done another comparison that bounds it. We can kind of go, yeah, we already know that you're bigger than this other thing in the list, so why would I bother comparing to you at all? All of these algorithms that are faster are kind of based on that principle. If you can see it, hopefully we'll be able to see it. So this is this divide and conquer stuff. It's an algorithm paradigm. You recursively break the problem down into subproblems of a related type. And then when it gets simple enough, you've got a direct thing that you can do. And then you just recombine results. We'll show you merge sort. I think I'll go through merge sort a little bit slowly. And I'll go through with a very bad example that has lots of like, if you're doing one of these for real, if you want to go and look at the Julia source code for quicksort and what it does, it will be super careful with allocations and doing things in place. So you're not copying memory. This thing copies memory all over the place. So that's why it's slow. If you want to do a fast version of merge sort, you kind of have to do things, you kind of want to reuse things that have already come in. So you're not allocating too much stuff. The whole idea is we want to kind of show what's going on. I don't know where I want to start. So merge sort, I think, think I talked about the von Neumann architecture in my first lecture. Von Neumann actually came up with merge sort. So like von Neumann in applied mathematics or mathematics is like one of these gods of the 20th century. He kind of did everything. He did fluid dynamics and number theory and quantum mechanics stuff. So huge thing. And then he got involved in computers as part of the Manhattan Project. And that's where that's where the architecture stuff comes from. But he also did some really first versions of algorithms. And this was one of the ones you can actually, I think pretty sure it was this one. I've actually seen his implementation of this, and it's kind of interesting to see, you know, if you go on a historical version of this, it's really interesting to go and see. There's lots much better. There's like the modern implementation of this stuff is much, much better. And this is a fairly terrible example to start with. The idea of merge sort, I wanted to show it to you first. So I can talk at a picture rather than talking at code to start with, so you get the idea. What the idea is we kind of want to break the array in half, and then in half again, and then down into constituent elements. This is this divide and conquer thing. So if we're going down, I'm going to split this, split this, split this, and then we sort them when it's just one comparison. And then we take the sorted lists, the small ones, and sort them together. So for this one, I never need to, when I'm comparing, I don't need to compare 43 to 27 because I know it's bigger than 3. So I kind of just need to, oh, maybe that's a bad example. I never can need to compare 38 with 3 because it's already know it's in this first one in this list. So if I've compared it with 27, I never need to really compare it with 38 unless it lost. So there's like some of these drop away. Some of the comparisons you're going to have to do drop away as you go down into the list. So the whole idea is that we do these in a go. We're going to split, 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 sort these little ones, which is really easy. And then as they come back in, we'll just kind of go back into place as we sort them as we come back up. That's what this idea is. So sorting this guy is much easier because some of the comparisons are done for us. So it gets the n log n scaling by this divide and conquer strategy. Is that clear? Yeah. Nobody looks unhappy. We'll just go through the code. Hopefully we can see it. So did we click on that? I don't think there's that's basically the basic idea of merge sort. So merge sort's kind of easy to understand. That's why we'll talk about it. You're doing quicksort itself. Similar-ish idea, but instead of breaking up arrays and then recombining it, you're gonna be funky and do it with just little pointers to array locations rather than doing that sort of stuff. So this is a recursive algorithm. What we do, first of all, we take the input data, work out its length. Hopefully this one's obvious. If it's length 1, do we need to sort it? No, so give up. That's this short circuit evaluation and return data. If it's that, program stops, game over, done. We've got to split this into 2. We have this div, hopefully you've seen that one. Oh, backslash, what am I doing? Anyway, slash div. This is the integer division. So it'll give you quotient from integer division. So this is like without the remainder. So because it's an array, you kind of have to split it on the odd case, the case that the array length is odd. Kind of have to break ties. We'll use this algorithm to go like, yeah, cool. You go on that side, you go on that side. So what we're going to do is it's a recursive algorithm. So these came up before. I've already forgotten what it was. We were talking about recursion, factorial. That was the one. We did it with factorial. Functions can call themselves. So what we're going to do is we're going to give my merge sort to the first half of the data. That's up to this div 2. And then we're going to go to the next item to the end. Yep, that's the top half. And then we've got a new data vector that's this L-type data, blah, 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 length data. So this is where new results come to. So this is basically that picture. I think I don't want it. It's a really lovely picture for something so simple. So this first bit, we're just going recurse, recurse, recurse down to the bottom. Then we're going to kind of go just interleave them on the way back up and so hopefully dodge a bunch of unnecessary comparisons. I think there's probably a better way to do it. So we need to do a little bit of index trickery. This is kind of nasty. I think there's probably a better way to do this. If anyone wants to do a better way to do this, wants to go off and do this, they get bonus points from me. I don't know if it counts for anything, but I'd be impressed. If you can go off and do this a little bit nicer, because I think this is kind of gross. Running indexes of where the bottom and the top of the arrays are. So we'll loop on indexes of destination array if bottom array is finished, blah, 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 blah. I think the interesting bit we want to do, so data new, data top. So B is greater than length data bar. These are kind of useless. So the real bit is this one where we've got these running indexes. This is this bit of kind of like interleaving them as they come back up. You kind of want to go, I've got the data from the bottom bit and the data from the top bit. And I want to do one through those running indices. I want to go like into the next array. What do I put in next? So the other bit of logic's a bit, just kind of throws you, I'd say. So it's basically when I'm coming up here, I've got like 27 and 3. I want to know what do I put into this section. So I've got like, cool. This one goes into here. I'm going to increment this index. So when I do my next comparison, it's going to be between 27 and 43. 27 is the smallest. Increment this one to 38, blah, blah. That's what that yucky bit of logic in the next bit's doing. It's kind of easier to see in a picture, but that's what we're kind of doing. So you thread this through and you increment, otherwise you increment this other one. If you stop, you just kind of read them in from the rest. That's it. Cool. Any questions on that bit of code, or is it? I kind of think it's not the nicest. Having this little bit of index games is kind of disgusting. But this idea of like, I think having these logics, this logic here is kind of less helpful. It's like, this is the main comparison that's interesting, is where you're going to want to go like, I've got these two arrays that I've already sorted from the layer down, and I want to put them back together. Cool. I think that's fine. So again, 1 million integers, we want to check. So you can copy this into your thing. We just made that function. Hopefully you do some testing that it actually works. So data. Oh, looks like it does the right thing. So in this case though, it's not a mutating one. So before we had, like, when I showed you the bubble sort one, I had the exclamation mark. The exclamation mark is this hint that this thing is going to be changing under your feet, so be careful. We haven't implemented this one this way. We've just made this data new. That's a vector of L-type data, undefined length, or undefined values, but length data. And we're going to write values back into this array. So this one is not mutating, unlike the other one. Hopefully equals sort data. It's true. So it's doing, it seems like it's doing the right thing on minimal bit of testing. Be interesting to try and break it. Built-in sort. So yeah, if we do this one, we'll just see if this is true on my computer now. Let's go rand 1 to 1e. This, oh, sorry, I just want that. Oh. So at time. So that guy needs to suppress the output. So about 0.4 of a second for that one, whereas built-in sort will flog it. Cool. So you got that first runtime thing. Or maybe not, actually. That's interesting. Anyway, so the difference here, and this was this thing about, this is not a super careful implementation. When you're trying to make stuff fast, you have this algorithmic problem where you're going to go like, order of operations, I kind of want it to scale the right way. What's that? Yeah, that's the thing, is like, this is allocating a lot of stuff. It's actually allocating 500 megabytes of stuff. And that thing I was saying about GC enabled true, that funny little magic spell, if you're getting this warning that it spent 5% of the time on garbage collection, you're kind of in trouble. So that means it spent 5% of the time just cleaning up all this memory you've thrown around all over the place while you were doing stuff. So if you're trying to be really fast, the ideal is to have no allocations and to have this nice scaling. So if you're trying to write something that's super, super fast, they're kind of the hints. We got similar timing. So like on my old computer, it's like 0.4 of a second, lots of allocations, built-in sort is, 0.05 of a second, super fast. This is where it's going to get a bit magical, and I'm going to intentionally leave it magical because it's not an algorithms course. But how you analyze this stuff can actually be really complicated for this sort of problems. But luckily, you can point to a known result. It's kind of got this ridiculous name called the Master theorem. I don't think it's named after anyone called Master. That would be less offensive, but I don't think it was. It's these two people, or three people, sorry, in the 80s, 1980s. So not that old as well. So like I was saying, this is all super clever stuff to come up with this stuff. This general result was only done in 1980 for how you would actually analyze the runtime of these types of programs. So they solved a much harder problem of recursive type problems. There's kind of like a plug-in theory for what you think the asymptotic runtime is going to be. So this is kind of like a hand-wavy proof. This is super hand-wavy, but this is a super hand-wavy course. We're going for breadth, not depth. So don't be too upset. But there's three things you want to do. You got to like sort this little bottom list, sort the top list, and then merge the data. So you can come up with a recurrence relation for how the main problem turns into the sub-problems of this recursion level. So what you do is you go like, I've got an array of length n. So the time to sort an array of length n is I'm going to split it in two and do it twice. So each of those have length n on 2. And then there's this order n operation, which is the last little bit, which is the time to merge two sublists. So yeah, the merge is of order n. So that's when you're going to put them back together, how many operations you have to do. And because we keep the array indexes, we only have to go through once. We don't have to go through more than once because they're already sorted. The general master theorem, I think they've changed the Wikipedia page on me. Basically, it's just like you need to know these coefficients A, B, and what order this Fn step has. And then it's basically plug that into the main result and it tells you what the main thing is. I'll leave that for you to go through, but basically a bunch of conditions in it. Plug it in and it gives you the answer that it's n log n. Hopefully you can see this though. So my intuition, again, I always think it's good to stare at these kind of pictures if you don't quite have it in your head. Dividing is quick. We're just going to cut it into bits until it's small. Then we're going to do these little sorts. So there's the time, we're going to split it, split it, split it. The main acceleration happens because this thing of like 43 is never going to get compared with 3, unlike bubble sort where we're sweeping through every time. So we've dodged a whole bunch of unnecessary comparisons. It's kind of the super, super hand-wavy version of n log n. Cool. If you wanted to do it, yeah, it's in this case, it's kind of weird. Someone did the more general proof, so you can just go and kind of go like, hopefully this makes sense to you, that this recursion thing though, that we're going to split it in 2, and then we have to do it twice, and then we have this order n to reconstruct. So any of these type of divide and conquer algorithms are covered by the master theorem, so you can kind of just plug it in and go. Cool. Quicksort, I'm not going to say too much about because like lots of people have and it's part of the homework, but I think another version of this, it's all these like looking at all, just staring at these animations is kind of the thing I always do of like, again, we want to subdivide the problem and do it. It's actually got an old provenance. Again, these are all kind of old problems. So merge sort, sorry. Pretty sure that was von Neumann. Yeah, so invented by John von Neumann in 1945. Quicksort, much older, 1953. And this guy, Tony Hoare, didn't just do that stuff. He did a whole bunch of other things on, but yeah, lots of other things. very smart person. All these people were mathematicians trying to do stuff in the original days. Has anyone had a go at implementing their own quicksort yet? No? Oh, you have? So maybe I need to go a bit longer on it than I thought I was planning on if no one else has had a go. Again, it's this divide and conquer. I'm not going to do the implementation. Pseudocode. Good thing about languages these days is that like the code looks like pseudocode. This kind of looks a lot like Python. Again, it's this recursive algorithm. So you're going to pick a high and a low point, and then quicksort takes the partition and sorts them through. I don't think I actually want to say too much about this, apart from kind of want to leave that for you guys, and then we can talk about it later. So maybe that's a good spot. I think that one's too close to the homework for me to bother too much to say about it. But the same main thing of like, it's another divide and conquer algorithm. Instead of allocating arrays this time, we're just going to muck around with points to the array. And the good thing about this one is you can do in-place stuff, so it can be a lot faster. Interesting thing we talked about, maybe I didn't talk about this. We'll go to the sorting zoo. Back up the start. No, sorry. There we go. So sorting algorithms, interesting case. I say I'm going to give you sort of like advice, not details for this one, but heap sort, you've got to worry about the best case complexity, average case complexity, and worst case complexity. And memory matters too. This is the one I was saying I'm always there sitting watching top, waiting for the memory to run out before I go. Heap sort's kind of like robust in that like best, average, and worst case is always n log n. Merge sort is similar in that best, average, and worst case complexity is always n log n. If you're being super careful with memory allocations, like you're not allocating a new array every time, you're doing actual good implementation. Memory footprint for merge sort is bigger than heap sort, believe it or not. This guy, quicksort though, this is one that's interesting. And this one comes up nearly every time for people doing the homework about the worst case complexity. Worst case complexity for quicksort, if you're not careful, you can actually be n squared. But it's pathological. In this case, like usually it's when, depending on how you've chosen your pivot, you actually get a different worst case. And usually if you follow the notes, for the pivoting strategy, this one where you're choosing a pivot. If you choose a pivot like this, the actual worst case is often, I think for this case, if you follow this to the note, the worst case is a sorted array. So you'll actually, people when they're setting up their homework, if they follow this directly and they choose this pivoting strategy, when they try and feed in a sorted array, like if you run it twice, they'll get this thing of like, oh, I ran it once and it was good, and then I ran it again and it was really slow. It's because the pivoting strategy, there is actually an n squared case, and you can have this actually, you can run it, very unlikely to run into it with a clever choice of pivoting strategy, but does happen. So I think that's super interesting in terms of the complexity. Super well covered. I don't want to say too much because it's kind of straightforward and you can do it yourself, and you will. I think that's fine. Yeah, that's fine. So sorting, we've done the tool stuff already. So that's kind of like the end of this lecture, but I'll start moving on to the next lecture if everyone's okay with that. We'll just do a little bit of stuff. Any questions on sorting? Feel like you've seen it, done it to death and sick of it now? No? Okay, cool. Okay, section 4, we'll just do like 10 minutes of this so we get ahead, because we've got like, it's going to be a lot to go. So this part of the course is kind of getting into my area of numerics. This is like the stuff I find most interesting. I kind of dodged talking about floating point for as long as I could, and now we've kind of run into the case where we have to talk about it. We have to deal with it. Going to talk about data and basic scientific compute environment, like doing plots and pretty pictures and stuff. Numerics is covered by other courses in much more detail. Has anyone done any of these two courses? Math 3204? No? Or this one, there's a computer science one, I think. No? Oh, well, I can talk about it more then, because this is like my area, so I love this stuff. We're just going to do, again, this course is super hand wavy. We're just going to brush across the surface of things. We're not going to go too deep. There's more to data than you could think. This is going to be the boring bit. We're just going to talk about files and data formats. So a file on a computer isn't anything more than, like we talked before, it's just a collection of bytes. Data, code, they're all kind of the same thing at some level. They're all bytes plus interpretation. So we've got some Unix stuff. Make this bigger. My buffer didn't come in. Okay, so talked a little bit about Unixy stuff where we've got echo -n 1 2 3 4, and we're going to run that into this thing called textfile.txt. So ls to check what's in the directory. I've got this thing hopefully called myfile. So down here, myfile.txt. If I interpret this, if I look at it in a code editor like VS Code or Vim or whatever you want, myfile, it'll interpret it as 1 2 3 4 5. Because it knows about, it's interpreting it, because I've opened it in a code editor, it's interpreting it as a text file. It's interpreting it as text, so it's interpreting it as strings. So implicitly, we're kind of opening this thing and saying, this is text, please interpret it as text. If I had something, I won't do that because it probably won't work as the way I think it will, but you have other types of files like images, and if you could try and interpret them as text, and you'll just get junk. And I was talking about this a bit when I was talking about Git, is like this fundamental thing of like looking through line by line for diffing to find the differences between files and storing those diffs. It's like interpreting it as a text file, which is, again, different types of binary data. You kind of don't want to put them in Git. Cool. So, you know, we had this, I showed this in Julia. We can do it from the command line with this thing. This curl library is a way of like talking to web stuff. We're going to open a file called shakespeare.txt, and we're going to load this other text file in there, 16 meg, downloaded like a rocket ship. That's this thing. So if I go to this guy, shakespeare.txt, this is the eText presented Gutenberg project, blah, 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 blah. This was the thing I added in Complete Works of William Shakespeare. You can download it all, blah, blah, blah. It's got new lines and everything. So that's just text. Cool. So it's encoded as a text file. We'll just do these little commands, ls -l. Just gives you a bit more. If you do ls, it'll be kind of boring. It'll just say, yeah, Shakespeare's there. If you go -l, it will give you a little bit more information. This stuff's about file permissions. I don't know if I talked about chmod. You don't really need to know that, but in a Unix environment, different users have different permissions to do things with files. And so like, if it's possibly dangerous to run a program on your computer, or it's got some sensitive information, you might not want everyone on the computer to have access to it. That's the user, blah, 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 file size, date created, or date touched, I think it is, and Shakespeare.txt. Cool. We had head -4 Shakespeare.txt. If you want to see some, oh, who saw what I did wrong? Face. So if you want the first 4 lines, or the first 10 lines, or the first 20 lines, you might do that. Its friend is tail. If you want to see it, it's at the end. Kind of a useful thing when you're poking around with files. Okay. What's up? Why is it -4? It's because all the optional arguments have these dash. So it's kind of stupid. You kind of got to work with the tools. Again, tail minus minus help. Yeah. Yeah, maybe it's not so useful, but yeah, there's more stuff you can do. Follow is useful, but that's okay. That's when a thing's getting written under your feet. Cool. So that's text, you know, like you can look at it. We kind of looked at the strings. They're just like ASCII encoded things. Let's do something funky here where we're just going to go into a Julia session. And so we're going to open. This is probably not the way to do it, but that's okay. That's okay. I won't show you. We're going to open a file called mybinaryfile.dat. When you open, we're going to write into it. We're going to write into file a bunch of, we're going to cast these guys to 1 to 20 as int8s. And then we have to close this file or we're going to have trouble. So ls, there should be a thing here that we called mybinaryfile.dat. Mybinaryfile.dat. We should be able to do a symmetric operation of reading this thing in, but we can also kind of just look at it. Cool. Where am I? Print working directory. So this guy should be in the same spot. Should be a thing here called mybinaryfile.dat. Text dump. My binary file. So you guys should all be getting a bit more fluent with this stuff, but if you want to, you can go and convince yourself that the things I wrote into this thing make sense. With the hex dump, you know, it's all the same as how it is in memory. So like you're just serializing this thing to a file and that's what it is. Hex dump, blah, blah, blah. That's kind of it. So like there's not much to this. This is like a really boring warm up to it, but like data, the way they're represented in memory, you're just serializing them to a file. You can read these in, you can interrogate them with hex dump. I think it come up like why does it, like when we do like in uint8, if I do a uint for a number, it's like, it comes up as hex by default, and it's kind of like a strange thing of like, why is it hex? And it's like this compact way of representing bytes, because it's like a pair of hexadecimal numbers represents a byte, and you can kind of see. So one of these things, like why would you do this hex dump is, maybe it's something you've never thought about, but how does your computer know what a file is? It's just bytes. It's like data, you could interpret it anyway. I could try and open an image as a text file, and it's like, it doesn't make any sense. So it's going to be one of these things I never really thought about would be when I was starting, is like, how can you tell what's in a file from the file itself? And not all files have these things, but a bunch of files will have these things called magic bytes, where at the start of the file, there'll be a special signature. So what's one that you might have heard of? JPEGs. So at the start of a JPEG, you would be looking for something like FFD8, FFDB, blah, 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 or some one of these. So something about the encoding, they've put some special bytes at the front that let you know what the content of the file is. So anything that's like a file explorer can kind of like, rather than just going on the extension. So like I can call move Shakespeare.txt to Shakespeare. I can call it Shakespeare. I can do that. And I've got this thing called Shapesburg.png, but it's not a PNG, right? It's just bytes. I've just moved that file to another thing. If I try and open this with an image thing, it's not obviously not going to be an image. Will the file system recognize that that's a PNG? Hopefully not. Hopefully it's not that dumb. It does think it's an image based on the file extension. So you kind of got this hint that based on the file extension, what is it? But you've also got the content of the file itself. And that's it's kind of this messy thing of like, it can be hard to tell, like data is just data and without interpretation, you kind of don't know what it is. It's kind of an interesting thing. Anyway, that's the point where I think it's time to stop because I'm rabbiting. Any questions on that so far? Next lecture, we'll go on to JSON and CSVs, and then talk about actual floating point and scientific work environments. That will be tomorrow. Hopefully we'll get to floating point. Floating point is the more interesting bit. Okay. Thank you.
I have a question.